We got a lot of info coming your way today. Today we're going to multiply and divide some radical expressions. So multiplying, easy. You can multiply these no problem. The numbers outside the radical, just multiply them. Numbers inside the radical, multiply them. But you can only do the inside radicals with inside radicals, outside the radicals with outside the radicals. And then you want to make sure you break down any perfect squares that might be left inside those radicals. So if you look at example 1, 4 root 5 times 3 root 15. 4 times 3 on the outside is 12. Inside 5 times 15 is 75. So we have 12 root 75. Now, thinking of perfect squares that go into 75, that's 25 times 3. Square root of 25 is 5. So we have 12 times 5 root 3. 12 times 5 is 60 root 3. Cool. All right. You look at example 2. 7 root 16 times root 24. You could totally do 16 times 24, but look for things you know. 16 is a perfect square. The square root of 16 is 4. So this is just 7 times 4 times the square root of 24. And if you want to think of what's a perfect square in 24, it would be 4 times 6. So this is what we've got. There's some stuff to clean up here. 7 times 4 is 28. Times the square root of 4 is 2, then we have our root 6. 28 times 2 is 56, and then you got your root 6. All done. So much fun. Look at us multiplying radicals. All right. You look at try number 1 here. Feel free to pause and try. Now that's a negative 7. It's not minus 7. So we can multiply the stuff outside. 3 times negative 7 is negative 21. 72 times 2 is 144. Oh my gosh, I could square root 144. It's a nice whole number. It's just 12. So negative 21 times 12, I don't know. Negative 21 times 12, negative 252. No radicals on that. I'd love to show you guys a trick that I like doing when I'm multiplying and I get kind of a lot of them together. And it's rooted in this. If I had the square root of 5 times the square root of 5, that would give us the square root of 25. And the square root of 25 is 5. So my trick in my brain is like, if I have the square root of something times itself, it just comes out to the regular version of itself. Which makes sense, because 5 times 5 is like 5 squared, and square root and square are inverses, so they cancel each other out, so it would just come out to regular 5. But if I had like the square root of 71 times the square root of 71, I don't even have to think. It's the same thing. It would just come out to 71. I don't have to get the gigantic number and then try to figure out what's the perfect square in there. So, using a trick like that on example 1 here, look, it came out to 60 root 3. I'll write it down here so we can make sure we get the same answer. But when old Josh Plant is doing something like number 1 himself, I think, hey, do 5 and 15 have anything in common? Like, yeah, 5 goes into 15. So we have 4 times the square root of 5 times 3. And then even though 5 is not a perfect square, in my head, I'll think of 15 as 5 times 3. Now, we can multiply 4 times 3 is 12. And then we can do my trick. The square root of 5 times the square root of 5 is just going to be regular 5. And then we'll bring down our root 3. 12 times 5 is 60, root 3. Awesome, right? And here's where I like it. I'm going away from the notes here for a moment, but I want to show you this because I do find it helpful for myself, and I do a lot of these problems. Let's say I had 8 root 12 times 4 root 30. This is going to give us a huge number, but check it out. We got 8, we got 4. You could multiply those now, or let's just kind of separate everything. Can you think of anything that 12 and 30 have in common that isn't even a perfect square? 6 goes into both of them. That's like their greatest common factor. So let's just play a game here, and let's use 6, even though it's not a perfect square. 12 is 6 times 2. 30 is 6 times 5. And then let's try the old trick. 8 times 4, 32. Great. Root 6 times root 6 is just regular 6. And then all we have left is this root 2 and this root 5. So 32 times 6, let's see, 180, 192. And then root 2 times root 5 is root 10, and there are no more perfect squares in 10. Otherwise, we'd have 32 root 360, which that one's not too terrible either. 360, if you look, it's 36 times 10. Square root of 36 is 6, which would still get you 192 root 10. I'm just trying to show you all the tricks that I know how to do because sometimes math is complicated for me and I try to come up with shortcuts that work for my brain, and I just want to share that knowledge with you. So this is also an option. The book wouldn't tell you that though. All right. Now we have some old properties here. When we multiply with exponents, remember we have to add the exponents when you multiply that common base. So here, 8x blah 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 times 4 blah 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 blah. Let's multiply them first. 8 times 4 is 32. With the x's, we have x to the third, x to the fourth, that would give us x to the seventh. For the y's, we have 4 and 5, that would be 9. And then the z's, 1 and 3 would be z to the fourth. Great. So now we'll break it down with perfect squares. In 32, I know that's 16 times 2, and I could square root 16. Remember, with the exponents on the variables, it's got to be even. So 7, no dice. So we put 6 here, the leftover 1 goes with the 2. For the y's, we could put 8 here, and 1 gets left over. The z's, 4, that's even, so we could put them all there. Square root of 16 is 4, and remember we just divide the exponents by 2. So that would give us x to the third, y to the fourth, z to the second. We got our root 2xy, and we're done, but we're not done having fun. Here's one for you to try. Feel free to pause it and try it. If we multiply these together, it's 2 times 1 out in front, which is 2. For the a's, we'll have a to the 8th, b to the 4th, and then that c to the 1st. As far as perfect squares, there isn't one that goes into 2, except for 1, but we don't use 1. So the 2 is just going to go leftovers. A to the 8th, that's even. We could put them all there. Same with the b to the 4th. The c, we don't have any even exponents. It's c to the 1st, so it's got to go in the leftovers. Square root of a to the 8th, a to the 4th. Square root of b to the 4th, b to the 2nd. And then we got our root 2c. I'm beginning to see a pattern here. Oh man, so good. Now you cannot have radicals in the denominator. It's not allowed. So what we have to do is we have to what's called rationalize that denominator. We have to get rid of the radical in the denominator. It's not terribly difficult. But all of the examples are simplified. Circle the ones that need to be rationalized. So again, you can't have radicals in the denominator. So which ones still have radicals in the denominator? This one does. It's got that root 6 down there. This one has a root 7 in the denominator. And over here you got a root 3 in the denominator. So those would all require more steps. So here we go. So this is the trick I was just telling you. Like the square root of 5 times the square root of 5 is the square root of 25, which is just 5. So if you ever multiply it by itself, it becomes a whole number. That's the easiest thing you could do. So, but essentially what we're trying to do is we're trying to create a perfect square in the denominator that we can then square root, so it's a whole number. So if you look here, we have root 2 in the denominator. So we're going to multiply it by a root 2, and that'll turn into a whole number then. But remember, when you change a fraction, if you multiply the denominator by something, you have to keep it balanced and also multiply the numerator by that. So we're going to multiply the numerator by root 2. Now 5 times the square root of 2, you just mash them up. It becomes 5 root 2. The denominator, root 2 times root 2 is root 4, and then the square root of 4 is 2. So 5 root 2 over regular 2. Make sure, so we've got rid of the radical in the denominator, good. Also check if you can simplify the stuff out in front. 5 over 2 can't simplify, so that would be your final answer. And I'm fine with you if you go square root of 2 times the square root of 2 and you just go straight to regular 2, I'm fine with that because you're going to do these a lot. So this one's for you to try. It's got a root 7 in the denominator. Feel free to pause and try here. We're going to multiply it by root 7. We also have to do that in the numerator. That will give us 2 root 7 over the square root of 49, and then the square root of 49 is 7. So 2 root 7 over 7. See if you can simplify the non-radical stuff. 2 over 7? Nope. So that would be it. Do they get trickier than that? You bet they do. Oh my. Sometimes you might see them listed like example 5. That would also be the same as if it was listed under one single radical. So you could simplify radicals with radicals. You can simplify regular numbers with regular numbers. So here, if I simplified the fraction 3 over 6, that would be 1/2. Which then, if we split them again, it'd be root 1 over root 2. So I'd be fine with you going from this step just to simplifying it here. You can simplify radicals with radicals. Now the square root of 1 is 1. So we have 1 over root 2. We can't have a radical in our denominator. So we can multiply by root 2 over root 2, which will give us 1 root 2 over root 4. And look, the square root of 2 times the square root of 2 is regular 2. So we have root 2 over 2. Now some people are going to be tempted to divide that. You can't divide radicals with whole numbers. Only radicals with radicals, whole numbers with whole numbers. So this would be your final answer. Let's say you didn't do what we just did. I'd always recommend simplifying it if you can. But let's say we forgot about that. I'm going to leave that answer, root 2 over 2. So let's say you can only remember, hey, multiply it by itself. Root 6 over root 6. This would give us root 18 over root 36. And you're like, cool, the square root of 36 is 6. So root 18 over regular 6. And that's cool, but there's still a perfect square left in 18. That's 9 times 2. And then the square root of 9 is 3, so it would be 3 root 2 over 6. And then you could simplify the numbers outside the radical. 3 over 6. 3 goes into 3 once, 3 goes into 6 twice. So it becomes root 2 over 2, the same answer we got. I'd recommend simplifying it early if you can. You're just working with smaller numbers then. So look at this one, 2 over 8. Simplify that. That would be 1/4. So it would be root 1 over root 4. And then I could square root both of those. The square root of 1 is 1. The square root of 4 is 2. We don't have to rationalize a denominator. The roots are gone in the denominator. So make sure there are no square roots in the denominator. Make sure that there are no perfect squares left in the root. And make sure you simplify anything outside the radicals. So here we go. 4 over root 10. Easiest thing you could do is multiplied by itself. Root 10 over root 10. Up top, we'd have 4 root 10. Denominator, square root of 10 times square root of 10 is the square root of 100, which is 10. Square root of 10 times square root of 10 is 10. Square root of smiley face times the square root of smiley face is just smiley face. Lock it in your brain. There are no more perfect squares left in 10. Can you simplify the stuff outside? 4 over 10? Yeah. You could divide both of those by 2. 2 goes into 4 2 times. 2 goes into 10 5 times. So we have 2 root 10 over 5 for a final answer. Yay! Here we go. 5 over 15. Can you simplify that? Yeah. 5 goes into 15 3 times. So it becomes root 1 over root 3. Square root of 1 is 1. 1 over root 3. No radicals in the denominator. Times root 3 times root 3. So this would give us 1 root 3 up in the numerator. Denominator, square root of 3 times the square root of 3 is just regular 3. Yay! Look at us, we're just having fun. All right. Now, and again, an old exponent property, when you divide, you have to subtract the exponents. So simplify, get rid of any radicals in the denominator, and you'll be fine. Look at this. Square root of 49 over the square root of x to the 6th. I can square root both of those. They're both perfect, just like you. Square root of 49 is 7. Square root of x to the 6th is x to the 3rd. No more square roots. We took the square roots. But this one, a little trickier. Let's simplify what we can, though. What do 12 and 27 have in common? They're both divisible by 3. So if I did 12 divided by 3, it's 4. If I did 27 divided by 3, it's 9. And this is still all under a square root. Now the a to the 3rd over a, subtract the exponents. There's more up in the numerator. 3 minus 1 is 2. So there's a squared up in the numerator. These are also both perfect squares. The square root of 4a to the 2nd is 2a. The square root of 9 is 3. No more radicals, baby. You know what's crazy? I think we got 3 super nasty problems coming your way. And then we're done. Oh my gosh. 3 over root 6. There's nothing to simplify there. So we could always just multiply it by itself. Root 6 over root 6. Up top, 3 times the square root of 6 is 3 root 6. Denominator, root 6 times root 6, regular 6. Because for the 50th time, it would be the square root of 36, which is 6. Are there any perfect squares left in 6? No. We don't have a radical in the denominator. There's one other thing to check for. Can you simplify the stuff outside the radicals? The 3 over 6. Yeah. 3 goes into 3 once, 3 goes into 6 twice. So it's 1 root 6, over 2. Great. Hooray. Can you simplify 9 over 2 at all? No. If you want, 9's a perfect square. It's just 3. 3 over root 2. Great. Can't have radicals in the denominator. Root 2, let's multiply by root 2. Got to do it up top as well. So up in the numerator, 3 times the square root of 2 is 3 root 2. Denominator, root 2 times root 2 is just 2. There are no more radicals in the denominator. There are no more perfect squares left in 2. Can you simplify the stuff outside? 3 over 2? Nope. So just leave it. Last one. Now, if you want, you could square root a 16 right now. You can make it 4 over root 12, and then you could work on the 12. I wouldn't even recommend it. I would recommend, if you can simplify now, simplify now. Those are both divisible by 4. So 16 divided by 4 is 4. 12 divided by 4 is 3. So we have root 4 over root 3. Square root of 4 is 2. 2 over root 3. All right, now it's time to get to work. No radicals in the denominator. Times root 3 times root 3. 2 times root 3, 2 root 3. Denominator, root 3 times root 3, regular 3. No more radicals in the denominator. No more perfect squares left in the radical. Can you simplify the stuff outside? 2 over 3? Nope. So you're all done with the radicals.